Okay, so we're going to take a look at section 9.7, which is on a topic called Taylor polynomials. It was developed first by this mathematician named Brooke Taylor, and this builds on what we talked about in the earlier parts of the chapter with series. So it says, recall back in Calc 1, you may have been asked to find a tangent line approximation for a function at a specific point. So for example, if we look at this function, we got a cubic function here. And if I said find the tangent line at the point -1, -2, and then use that to approximate the value of the function -1.2. Let's start with the tangent line, okay? How do we find the equation of the tangent line? Well, we need a slope, of course, and we need the slope at the specific point, and then we need a point, and that gives us the equation of a line. Well, we have the point, -1, -2. How do we get the slope of at that point? We use the derivative. So the derivative, of course, is 6x squared plus 2x, and we're going to substitute in the -1 that they gave us, and we get a slope of 4. So my equation of the tangent line, I've moved it to slope-intercept form. Normally I say point-slope form is fine, but I think in slope-intercept form it's going to be easier to see what's happening here. So the equation of the tangent line at the point in question is y equals 4x plus 2. Now the second part of the question asks us to approximate the value of the function at the location -1.2. So if we were to substitute -1.2 into our tangent line, we get an approximation of -2.8. The actual value, if we were to plug in -1.2 into the original function, we would get a value of -3.016. So how far apart are these two values? That's what we're going to get into a lot in this chapter, is looking at the error. And if you remember, we talked at the last part of the previous unit about looking at error associated with a partial sum. This all kind of ties together. And our goal is to get these approximations to be better and better. So you can see if this is the actual value and our approximated value from the tangent line is here, we have some error associated with using that as our approximation. How could we make this a little bit better? Well, if instead of using a tangent line, what if we used a polynomial? So polynomial functions can be used to approximate other functions that we're maybe not so familiar with. So let's start with an example. And this was really, this was how they did things before we had the technology to work with these topics. So we're kind of giving you a background on where some of this stuff comes from. So take the exponential function e to the x. Let's find a first-degree polynomial. So think about the terminology here. A first-degree polynomial function in the format p sub 1 of x equals a naught plus a sub 1 of x. You don't have to remember all the notation here, but basically what I want you to see is that this is the equation of a line. This is a linear function. A first-degree polynomial would be a polynomial with degree 1. That would just be the equation of a line. So they want us essentially to find the equation of a line whose value and slope, so slope means derivative, right? Whose value and slope agree with the value and slope of the original function, f of x, at the location x equals 0. So let's take the polynomial, or I'm sorry, the original function, f of x equals e to the x. The value at 0 is e to the 0, of course, which is 1. What is the derivative of the function? Well, this is an easy one. That's just e to the x. And so f prime at 0 would also be 1. So our first degree polynomial, what did they say? They want it to agree in value and slope of the original function at the location x equals 0. So our first degree polynomial looks like this. So we've got 1, that's the y value, equals a naught plus a sub 1 times 0, because that's the x value, which means a sub naught just equals 1. So if we put all this together, remember the slope needs to be 1 as well at that location. The derivative of the function for my polynomial, let me back up just a second. The derivative of my polynomial, actually maybe look at it back here. The derivative of my polynomial back here would just be a sub 1. So what we want is we want a sub 1 to also equal 1. So our first degree polynomial for the approximation of the function that was given, centered at x equals 0, is p sub 1 of x equals 1 plus x. So 1 was the a naught value, and the coefficient on the x was the a sub 1 value, which was also 1. If we look at a graph of this, we've got our function, which was e to the x, and this maybe isn't the best quality graph, but we've got e to the x, which is the exponential function, and then we've got the tangent line at that same location, which is the first degree polynomial, p sub 1 of x equals 1 plus x. Our approximation is reasonably close at x equals 0, but what I want you to think about is what happens as we get further away from where x is 0. So this is the exponential function, and you can see as you get further away in both directions of x equals 0, our tangent line approximation pulls away from the curve, right? So it's not as good an approximation the further away we get from x equals 0, which is where we started. How could we get this better? Well, if we add more terms, so we did a first degree polynomial, which is really just a tangent line. If we added more terms, we're going to get a better approximation. So let's do this again, and let's do a second degree polynomial approximation. The values this time of the second derivative of the polynomial and the function must agree at x equals 0, as well as the first derivatives that we already did. So f of 0, of course, is 1. P prime of 0 would be f prime of 0, which of course would be 1. And p double prime would be the same thing, because e to the x, keep taking the derivative, you still get e to the x, would also be 1. So if we put all this together, and the idea here is I hope we're starting to see a pattern as we build here. So my second degree polynomial looks like this. A sub naught plus a sub 1x plus a sub 2x squared. All right, so where is all this coming from? We'll see later where we get these numbers from. So hang on, I'll explain all that in just a minute. But take my word for it for right now. This is the second degree polynomial for our function e to the x at the location x equals 0. Let's look at the graph of this. That's what I want you to see. So here's the exponential function is right here. Our second degree polynomial, let me go back for a second. This would be the equation of a parabola, right? So our parabola is right here. So you can see that as we move away from x equals 0, particularly in the positive x direction, the approximation is still pretty good. Even over here in the negative x direction, the approximation is still pretty good until maybe like right about here, and then the polynomial and the exponential function start to pull apart. How could we make this better? Well, we could add more terms. So the more terms we add, the better this approximation is going to be. So let's generalize this and say the nth degree polynomial approximation for e to the x at the location x equals 0 is given by this polynomial, 1 plus x plus a half x squared plus 1 over 3 factorial x cubed, and so forth, up to 1 over n factorial times x to the n. And theoretically, the more terms we add, or think as we take this to infinity, as the number of terms goes to infinity, the better our approximation is going to be, and the closer we get to the actual function e to the x. We could write this as an infinite sum. We could say this is the sigma from n equals 0 to infinity of x to the n over n factorial. Pause for a second and make sure you see that the terms I have written out here fit this infinite sum. And we have seen this before. So our polynomial has the form. So here's where you're probably saying, where's she getting all these numbers from? And you should be saying that because I haven't explained that yet. But here's what I want you to notice. Our polynomial has the form e to the 0, so that would be 1, plus e to the 0, which is the first derivative at 0, which would also be 1, plus e to the 0, which is the second derivative, which would also be 1, over 2 factorial, which is the same as 2, x squared, plus e to the 0, which would be the third derivative. Make sure you see where I'm getting these from, because the derivative e to the x is just its own derivative, e to the x. So each of these derivatives, these are all subsequent derivatives evaluated at 0, which of course is just 1 every time. And then over this pattern with the denominators. More generally, we could write it this way. So this is really what you want to highlight in your notes. This could also be written as f of 0 over 0 factorial, if we want to be thorough. 0 factorial by definition is 1, plus f prime of x at 0 over 1 factorial times x, plus f double prime of 0 over 2 factorial times x squared, plus f triple prime of 0 over 3 factorial times x cubed. And we could carry this on as many terms as we'd need to. So this is called the Taylor polynomial. So if we want to come up with a polynomial of the function f, so for any function at x equals a, so the center or the location where we're doing this is at x equals a, it's going to follow this pattern every single time. Now, in the last example, let me go back for just a second. Remember, we were evaluating it at x equals 0. So I just put x, x squared, x cubed, x to the fourth, and so forth. Notice that's what this says, though. If x is 0, then x minus a just turns into x. And so if it's centered at 0, it would look like this. But what I want you to see is this down here and this Taylor polynomial up here are the same thing, except this is a special case where we center it specifically at 0. And that's got a special name called a Maclaurin polynomial. That was named after a different mathematician who had to come up with his own name for it. And so if we centered at 0, it's called a Maclaurin polynomial. But the pattern is the same. And so what we did in the last example with the e to the x, we actually did a Maclaurin polynomial, we just didn't call it that. Okay. Let's do an example. Find the nth Maclaurin polynomial for the function y equals cosine of x. So we have the trig function y equals cosine x. Because it's a Maclaurin polynomial, that means we are centering it at 0. So what we want to find are successive derivatives for this function at 0. So start with f of x. F of 0, of course, is 1. Cosine of 0 would be 1. What's f prime of x? That would be negative sine. So f prime of 0 would be negative sine of 0, which is just 0. F double prime, so I want you to think about this before I hit the button. The derivative of negative sine x would be negative cosine x. So the second derivative at 0 would be negative 1. Fourth derivative, oh, sorry, I skipped the third. Third derivative, so the derivative of negative cosine x would be sine x, and the third derivative there would be 0. Fourth derivative would be cosine x, and the derivative there would be 1. Hopefully you see that there's a little bit of pattern here, right? So since trig functions we know are cyclical, it's going to follow this pattern. This cosine function is going to follow this pattern every time. 1, 0, negative 1, 0. 1, 0, negative 1, 0. That would be our pattern every single time. So if we put this together using our formula for the Maclaurin polynomial, we'd have f of 0. Go back and look at your notes. Make sure you see where this is coming from. Here, let me back up just a second. So I'm using this formula right here, okay? So f of 0, go back to all my terms here, and write all of these successive derivatives out. Don't try to do them in your head. Write them all out when you do these problems. F of 0 would be 1 plus f prime of 0 times x minus f double prime of 0 times x squared over 2 factorial plus f triple prime of 0 times x cubed over 3 factorial, and then the pattern starts over, and it proceeds like that. Now, you'll notice that all of the odd-powered terms are going to zero out here. So we could clean this up and write it this way so that we're just using the even-powered terms. So this would be the nth Maclaurin polynomial for cosine x. And you can go up to x to the n or whatever you want to, but if you want to just put dot, dot, dot to indicate that it's going to keep following in that pattern, that's okay too. What does this look like? So let's take a look at how the graph of the original cosine function compares to the graph of the polynomial that we just came up with. So here's the original cosine curve, right? The regular old cosine curve that we're familiar with. So if we were to just graph the first degree polynomial, so the first degree polynomial, actually, yeah, the first degree polynomial would just be 1. So that would be the tangent line at x equals 0. Add a second term, and we get the parabola like this. And what I want you to look at is what's happening as I keep adding terms. How good is my polynomial at approximating that cosine function? So the more terms that I add, hopefully you see that the better my approximation is getting. So the more my polynomial is actually looking like that cosine curve itself. So there's the one taken out to x to the 10th, this one in blue right here. And it's pretty good. I mean, all the way out to x equals 5, negative 5, almost out that far, you're getting a pretty good approximation of the original cosine curve. So the more terms we add, obviously the better our approximation is going to be. So let's do another one. This time we want to find the nth degree Maclaurin polynomial for the function y equals cosine of 2x. So start by writing out successive derivatives. Here's the formula again for the cosine polynomial. Oh, actually, okay. So we could do this using second or successive derivatives. That's okay. But in this example, what they're showing you is that if you already know the formula for the basic cosine polynomial, you can come up with the one for sort of a shift of that function by making appropriate substitutions. Here's what I mean. This is the polynomial for the original cosine x. That's the one we just came up with in the last example. They want us to find the polynomial for cosine of 2x. So literally what I can do is substitute all these x's with 2x. So instead of starting over with successive derivatives, which you could do, we can use what we already know. Take a look. So I've replaced all the x's with 2x. Now, obviously, these can be cleaned up and we can simplify it. I don't care about simplification when you do these, as long as you find the pattern. If it helps you to simplify to find a pattern, that's okay. But leaving it unsimplified is perfectly fine. So this would be the infinite or the nth degree Taylor or Maclaurin polynomial for the function y equals cosine of 2x. Let's try this one. They're asking for the third Taylor polynomial for the function f of x equals sine x, expanded around c equals pi over 6. So this one's a little bit different now because we're not centering it at 0. We're centering it at the location pi over 6. So let's go ahead and start with successive derivatives for the sine function. So f of x is sine x. So we need to start with f of pi over 6, which is sine of pi over 6, of course, which is 1/2. The derivative, first derivative would be cosine x. So f prime at pi over 6 would be square root of 3 over 2. The second derivative would be negative sine x. So the second derivative at pi over 6 would be negative 1/2. The third derivative would be negative cosine x. So the value there would be negative root 3 over 2. And then it's going to start over. So when we get to the fourth derivative, we're starting over back to the original function. All of these are about patterns and making sure you see the pattern when you write these out. So let's make sure we see where everything's coming from. We've got f of pi over 6 plus f prime of pi over 6 times x minus pi over 6. So this is the formula for my Taylor polynomial, plus f double prime of pi over 6 over 2 factorial times x minus pi over 6 squared, plus f triple prime of pi over 6 times over 3 factorial times x minus pi over 6 cubed. And by the way, I just realized I said we'd see a pattern and we'd start over. And we could keep going. But they did ask us for the third Taylor polynomial. That means the third degree. So since this is my third degree term, that's where I'm going to stop my polynomial at. So now I just need to fill in the values that I had. So f of pi over 6, f prime of pi over 6, and so forth gives me these numbers right here. So my polynomial is 1/2 plus root 3 over 2 times x minus pi over 6, and so forth. I did a little algebra to clean these up, but make sure you see that all I'm doing is substituting these values up here into the formula for the Taylor polynomial. And here's kind of a rough sketch of what this looks like. So remember, we have our sine curve goes through the origin just like this. And so our polynomial is the one below it. And you can see out until about right over here, it's a pretty good approximation for the actual sine function. Our polynomial is a pretty good approximation. Let's try this one. Use a fourth Maclaurin polynomial to approximate the value of the natural log of 1.1. So Maclaurin means we want to center it at 0. A fourth polynomial means they want us to use the fourth degree polynomial. So it says we could find an approximation for f of x at the natural log of x centered at 0. However, natural log of 0 doesn't exist. That's not possible because there's a vertical asymptote, remember, in the natural log function at x equals 0. And we want to approximate it at 1.1 in just a second. So why don't we go ahead and center it at, or use the function shifted natural log of 1 plus x and center that function at 0. So if we can picture the natural log function of 1 plus x shifts the natural log graph to the left 1 unit. So let's use this as our approximation or our function that we want to work with. So remember, for a Maclaurin polynomial, we're going to center that at 0. So make sure you're clear. I'm changing the function. I'm not really changing the function, but I'm using the function, instead of natural log of x, I'm using the function natural log of 1 plus x, because that I can center at 0. I can't center the natural log at 0. So I have to use some kind of shift to help me get there. So the polynomial formula for a Maclaurin polynomial, remember, is this. This is the basic formula. Let's find successive derivatives. Start with f of 0. So that would be f of 0 plus 1, which would be natural log of 0 plus 1, which would just be natural log of 1, which is 0. The first derivative would be 1 over x plus 1 using a chain rule, and approximating that at 0 would just give us 1. The second derivative using a chain rule would be negative 1 over x plus 1 squared, which would just be negative 1 when we plug in 0. The third derivative would be 2 over, again, using a chain rule, 2 over x plus 1 to the third power. Plugging in 0 gives us 2. And then the fourth derivative, because we're asked to do a fourth degree polynomial, this is where I'm going to stop, would be negative 6. So if we write all of that out and put it together, this is what my fourth degree polynomial looks like. Again, you can clean it up or not. It's really up to you. They were asking us to approximate the value, remember, for the function natural log of 1.1. Well, if I'm using the natural log of 1 plus x, that means my x value is going to be 0.1. So I'm going to plug in 0.1 for my x values up here, and I'm going to get an approximation of 0.0953. The actual value, if you were to plug into your calculator the natural log of 1.1, would give you 0.0953101 and so forth. Do you see that these are pretty close? So that fourth degree polynomial was a pretty good approximation. Here's the actual value down here. And then, here is our approximation using the fourth degree. When referring to Taylor polynomials, we may talk about them in terms of the number of terms. So you may be asked to write a polynomial with 3 terms or 4 terms or whatever. We might be asked to write about it in terms of the degree or the order. The order refers to the derivative. So like a third order polynomial would be something using the third derivative, going up to the third derivative. The cosine, here's just a little example. The cosine x Maclaurin polynomial looks like this. If we stopped here, we could say this is a polynomial with 3 terms. We could also call it a fourth order polynomial because it would have been found using the fourth derivative for that cosine function. We could also call it a fourth degree polynomial because it stops at x to the 4th power. Okay, let's take a look. This is the next part of 9.7. Now we're going to get into some notation here that's going to be a little bit intimidating. I don't want you to get too worried about all of this notation. I want you to focus on the big picture, which is approximating error using that same concept we talked about at the end of the last unit. And I'll show you what I mean. So let's take a look. So Taylor series are used to estimate the values of functions. Again, this is a little bit more of a theory base on where this comes from. A lot of times, of course, today we use technology to do this, but we want to know how useful our estimate is by looking at the error associated with our estimate. So a Taylor polynomial we can use to estimate the value of a function. So for example, if I go out to like the 3rd degree or the 4th degree, we know that it's not the same as the actual function like we saw in the graphs a few minutes ago. There's always some error, and that error is called the remainder. We want to know how close that remainder is to the actual true value. This is an idea to keep in mind here. The actual function f of x is always equal to whatever your polynomial approximation is up to the 3rd term or the 4th term or whatever, plus whatever terms you don't include become your remainder. So we want to figure out how good our estimate is based on how far apart our remainder is from the actual function and our estimate. So Taylor's theorem with a remainder looks like this. So if we have our Taylor polynomial, f of x is equal to f of a plus f prime of a times x minus a, and so forth, up to whatever nth term we stop at. Any terms we don't include after that become our remainder. Another mathematician, Lagrange, came up with his own version of this remainder. So in this box right here, this is kind of an important point. The remainder can be thought of as, all right, so connect this to what we did at the end of the last chapter. The n+1th term evaluated at c, and I'll explain what c is in just a minute, over n+1 factorial times x minus a to the n+1th power. Think about where n+1 is coming from. If I stop at n, do you agree that n+1 would be the next term? And so that's going to be where we get that remainder from. So it's the remainder after the partial sum up to a certain point where c is between a and x. A is what we're centering it around. Don't forget, x is the number we're approximating. And in just a second, I'm going to tell you a little bit more about c. Don't get hung up on what c is. Here it is again, same thing. This is also called the remainder of order n, or the error term. This is essentially the next term in the series. C has been replaced, but a has been replaced by the number c in that expression. But the main point I want to make is that this is the next term in the series after we stop our polynomial. If we stop on the 4th degree term, this error, or this remainder, I should say, would be bounded by that next term, the 5th term, for example. We don't always know what c is, but sometimes we can find a maximum value for c. And so this formula, again, I'm throwing a lot of notation at you. You don't have to memorize any of these formulas, but it's the big picture I want you to think about. This formula, Taylor came up with this thing called the inequality that says the remainder that we're talking about, so the cutoff term after where we stop, that remainder, absolute value of that, is bounded by m over n+1 factorial times x, absolute value of x minus a to the n+1. M is the maximum value of what that could possibly be. So the highest potential value for that n+1th term, that's our maximum value. So our remainder is always going to be less than or equal to that. So this kind of gives us like an upper limit or an upper buffer for what our remainder will be. So let's do an example here. Let's kind of put this together. Find the third Maclaurin polynomial for sine x and use Taylor's theorem to approximate sine of 0.1 using your polynomial, and then talk about how accurate that is. Let's just do the Maclaurin polynomial first. Okay, so what we did in the last PowerPoint, f of x, start with successive derivatives. F of x is sine x. If it's Maclaurin, we're evaluating it at 0, so that would be f of 0. I went ahead and wrote all the derivatives out first. So f of x is sine x, f prime is cosine, f double prime is negative sine. The third derivative, f triple prime, is negative cosine. If we put in 0, we get 0, 1, 0, negative 1. So right away you see there's a pattern to this. I'm stopping here because they said the third Maclaurin polynomial, so that's the polynomial that's based on our third derivative, which is this term right here. That gave me a value of negative 1. So we put this together using our Maclaurin polynomial formula. We get x minus x cubed over 3 factorial. So let's approximate it using, or let's approximate sine of 0.1 using our polynomial. Taylor's theorem says that we're going to, that our original function, s sine of x, can be written as our polynomial plus the remainder associated with using that third degree polynomial. That remainder is bounded by the 4th term. So the 4th derivative over 4 factorial times x to the 4th power, where c is between 0 and 0.1. Okay, I'm getting that 0 and 0.1 from, let me back up for a second. 0 was what we centered it around. 0.1 was the number we wanted to approximate. Okay, so that c value is going to help us get that upper limit or that maximum value. So sine of 0.1 using our polynomial, if we plug in 0.1, we get 0.1 minus 0.1 cubed over 3 factorial gives us an approximation of 0.099833. Well, how good is our approximation? How high is this bounded? So our remainder, which is equal to that 4th cutoff term, that 4th degree cutoff term, what is the maximum value for, well, let's do it this way. The 4th degree, 4th derivative, I should say. Let me back up for a second. The 4th derivative, let me go back to my list. My third derivative was negative cosine x, so the 4th derivative would be positive sine x. So my 4th derivative right here is sine x. I'm using c. You can call it x, it doesn't matter, over 4 factorial times 0.1 to the 4th power. So here's the idea. This is bounded by, this is the big picture, highlight this in your notes right here. This is bounded by the maximum possible value for the 4th derivative, which is sine x, sine of c, whatever. C is like a dummy variable. The sine function over 4 factorial times 0.1 times to the 4th power. So what is the highest possible value that the sine function can take on? Think about your basic sine curve, sine and cosine for that matter. But your basic sine curve ranges from -1 to +1, right? Think about your sine curve, picture the graph in your mind. The highest value for your basic sine curve is 1. So this max value is 1. And so this remainder is bounded by 1 over 4 factorial times 0.1 to the 4th power, which is just 0.1 to the 4th power over 4 factorial. And that gives us this number right here when we change it to a decimal. So that means our remainder is less than, or our tolerance, if you want to say that, is within 0.000004. So our estimate of 0.099833 is slightly under the actual value by how much? By that amount right there. So I'm going to take that 0.00, that number, a remainder, and I'm going to add this to the 0.099833, and I'm going to subtract it, and I'm going to get a boundary, excuse me, a boundary for the actual value for sine. So the sine of 0.1 we know is between this number and this number. Let's try another one. Use Taylor's theorem to obtain an upper bound for the error for this approximation. So we have e to the 1st power. So we're using the function e to the x. And you may or may not recall from earlier in the PowerPoint, we wrote out the Maclaurin polynomial for e to the x. And it looked like x, or 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so forth. Okay? If we plug in a 1, we get 2.717. So writing out, it says, note that we are approximating e to the 1st using a 5th order polynomial. And how do I know? Because I stopped at the 5th derivative term in my polynomial. So think about what's our remainder bounded by. Our remainder, I should say, is equal to or equivalent to the next term that I stop at. So that would be the 6th derivative of e to the x over 6 factorial times x minus 0 to the 6th power, because we're centering it at 0. So the 6th derivative for e to the x would be e to the x. I'm using c again. Remember, c is the dummy variable. Don't worry about it. But what I want you to think about, because I need to know the maximum value for e to the x. That's what I need to know so I can get an upper bound for my error here. On the interval 0 to 1, so what I centered it to what I'm evaluating, right? I'm evaluating it where x was 1. I centered it 0. On the function e to the 0 power, or e to the x power, on the interval 0 to 1, what is the maximum value? Where is that going to occur on that function? And let me see if I can, I was going to say, no, I thought maybe I had a way to draw this. Let me switch over for just a minute to my iPad here and see if you can see that. Go to my whiteboard for just a minute. Okay. All right, so here's what you want to think about. If I were to graph the function e to the x, right, your basic exponential function, and we're only concerned with the interval from 0 to 1, okay, so from here to like maybe right here. On that interval, where is the maximum value? Well, this function is increasing the entire time, right? So I know that if it's an increasing function, the highest value, the location for the highest value is going to be at the right endpoint where I stop. So my max value is going to be right there at the right endpoint, which is e to the 1st power, okay? So let me go back to the PowerPoint here. Here we go. Okay, so 0 is what we centered on. 1 we knew was what we were approximating. So since this is an increasing function, we know that the max value is going to be at the right endpoint, which is e to the 1st power. So our remainder is bounded by e to the 1st power over 6 factorial times 1 to the 6th power, which is 0.00378. Remember, our approximation was 2.717. Using our polynomial, that was our approximation. So if we put that into our calculator, we get 2.71828. We take the difference between the actual value and our approximated value using our polynomial. We get an error, move this out of your way, we get an error of 0.00128. And notice that that error is less than our boundary right here. We said our max error was here, our actual error was here. So this remainder gives us an upper bound for how good we think our approximation is going to be.